Photo ID is often used to confirm an individual's identity. Although this task is easy for familiar faces, error rates of around 20% are common if the person is unfamiliar. Of course, because of the coronavirus pandemic, many people now wear face masks in public. Soon it's quite likely that someone will need to be identified from a photo that shows them wearing a mask. Masks are known to impair recognition memory for previously seen faces, but just how they affect performance on these perceptual matching tasks is unclear. And of course, it's not just humans that have to perform matching tasks. Automated face recognition or verification systems, which are typically deep neural networks, are increasingly common. But many of these systems are not designed to identify masked faces, which is typically a challenging task. So our aim was to investigate how face masks affect the performance of humans and a naive DNN on perceptual face matching tasks with both familiar and unfamiliar faces. Our study had a between subjects design. Participants were recruited online and they were randomly assigned to complete the entire experiment in either the control, mixed or masked conditions, which are shown in the figures on the right. The masks were photoshopped over the original images. There were two face matching tasks, but they both had the same procedure. Two faces were presented on screen simultaneously, and participants indicated whether they showed the same person or two different people. The Glasgow face matching test uses unfamiliar faces. 20 of these trials are true matches, and the remaining trials are mismatches. We created the Sterling famous face matching task for the current study. Half of these trials are unfamiliar face pairs, which in this case are amateur models, but the task also features familiar face pairs, which are famous celebrities. At the end of the task, all participants completed a recognition test for these faces, and we only analysed data from the trials that the participant could name at least one celebrity in each pair. For human performance, we focus on the signal detection measures D' and criterion C. D' is a measure of sensitivity, which is how well someone can distinguish matches from mismatches. Criterion is a measure of response bias, which is whether someone has a bias to respond match or mismatch. The error bars show the standard error of the mean, and the effect sizes in the text are Cohen's d, not to be confused with D'. The top panel shows that across both tasks, sensitivity falls from the control condition to the mixed and masked conditions, which don't differ from each other. These are all large effects with Cohen's d values of at least 1.02. Surprisingly, the impairment is actually slightly stronger for familiar faces than unfamiliar faces. The bottom panel shows that the masks also affected response bias. Participants developed a bias towards responding mismatch in the mixed and masked conditions of the Glasgow task, whereas a bias to say match was increased in the mixed condition for the familiar faces of the Sterling task. The DNN gives two outputs for each pair of faces. The first is a binary match or mismatch decision. The second is a similarity rating, which the binary decision is based on. This particular DNN declares a match for faces with a score above 40, which is shown in red. The left graph shows classification accuracy as a percentage of 20 trials in each stimulus condition. The DNN achieved accuracy of 95% or more in each stimulus condition for the control and masked faces, but it made a number of errors in the mixed condition for the Sterling task's match trials. The similarity ratings on the right show the source of these errors. In match trials, control pairs were rated to be more similar than the masked pairs, which in turn were more similar than the mixed pairs. In the Sterling task, the average similarity for the mixed condition fell to threshold, which caused these errors. For the Sterling task's mismatch trials, the control and mask conditions were seen to be more similar than the mixed condition. Face masks clearly impair human face matching performance, but our study doesn't say why. One possibility is that masks interfere with the holistic processes that contribute to face perception. Surprisingly, the DNN performed very well when both faces were masked, even though it had not been trained to identify masked faces. But accuracy fell in the mixed condition due to the reduced similarity ratings. Unlike humans, DNNs use a fixed decision threshold, which means that they will be prone to errors with masked faces. Our main paper shows that some commercial face recognition systems are severely impaired by face masks, meaning that it can't be assumed that naive DNNs can be used to recognize masked faces.